Well, first of all, I'd like to start by thanking everyone from Voxel 51 for organizing this. Truly a really nice opportunity for us to showcase our work. So today I'll be presenting our work, Range Retrieval Augmented Neural Fields for Multi-Resolution Geo-Embeddings. So this is work that was done at WashU in our MVRL lab under Dr. Nathan Jacobs. So before starting explaining my work, I'll quickly spend some time trying to explain about the general field that I work on, which is sometimes referred to as GeoAI, and that'll help me kind of motivate why what I'm doing is relevant, right? So we're very familiar with this setup where we have image and then we want to train some model and then we want to do something cool with this, right? Sometimes it's classification, segmentation, etc. And another setup that we see often is this setup where we have some text and then we want to train a model to do something cool with this text. Like these are developing your chatbot, sentiment analysis, etc., etc. And then there can be combination of these models to do some multi-model tasks, such as visual question answering. Given an image, you want to ask questions about the image, and you want to get some insightful answers. And when we're talking about GeoAI, a lot of this part remains the same, where we still want to train models and do a lot of the things that are similar to what I described. What changes is mostly in the data side. And today in this presentation, I will talk a little bit about what kind of data do we usually deal with and what are the interesting challenges that arise as the data changes. And yeah, let me go a little bit deep into what I mean by GeoAI and what is the kind of data that we use, right? So GeoAI, very in a broad sense, it usually refers to like a bunch of tasks where we're using AI to solve geospatial problems. And then there's another definition of what a geospatial problem is. And one of the best ways I describe it is these are problems that have a relation to some point on Earth. So let's take an example. Let's take this red point right here on Earth. And so there's a bunch of questions, such as, is this point a forest, water body, or urban? Like, what kind of surface is this point? So this is the problem of land cover classification. Or you might ask the question, how crowded is this point? So a problem of population density estimation. Maybe you're interested in understanding if there's been a disaster, such as an earthquake or a flooding in this point, which is disaster recognition. Or you might be interested to understand it. Has there been any temporal changes in this point in the past few days, months, years? And this is an established problem of change detection. You can also have generated problems, like you might ask question, given a point on Earth, what would an image taken at this point look like as well? And there are also some other problems which are in an inverse setting of this. So you can have a problem, and then you're asked to find what is a point that would satisfy a given problem. So there's a very well-defined task of geolocalization, which is that given an image, can you geolocate where in the world this image was taken? Or you can have a task where of species distribution modeling, where you're given an image of some species, and then you're going to ask the question, where in the world the species would be found. And this, instead of giving one location, you'd probably have multiple location across the world that satisfies this condition. And so these are just a very small subset of a large number of tasks that falls under this GeoAI umbrella. And as I've been giving a high-level overview of the kind of tasks that we usually deal with, hopefully one thing was clear is that points on Earth tend to be an important data modality in geospatial problems. So almost any geospatial problems have a correlation to a point on the Earth. And so there's a natural problem of how are we going to represent these points on Earth if we're going to feed them into some neural network model for downstream tasks. So in the natural setting, they're usually represented as a two-dimensional 2D vector represented by longitude and latitude, which we're, I think, most familiar with. But experimentally, we have seen that this tends to be very limiting. This is not high information dense. And so if you just take latitude, longitude information and feed it to neural networks, they tend not to be able to fully utilize this information. And so our work involves learning more powerful representations to represent points on the Earth. And so just like you have Dino for representing images, BERT, Alberta, or all of the other text models for learning representations of text, we also want to learn foundational models that allow us to represent these points on the Earth. And that is the line of work that I am interested in and what this paper is about. I'll start by saying that we're not the first people to do this. There's a long line of work that already does this. And generally, there tends to be two ways that you can solve this problem. So the first approach is called analytical methods. So there's no learning involved in these methods. You usually use some existing functions and then use those functions to learn a high-dimensional representation for the geolocation, right? So there has been approaches that use Fourier features to represent these locations, and there's been approaches that use spherical harmonic basis functions to represent these locations. And we have seen that both of these work tremendously well and are far superior than just naively using the 2D representations. However, I will not be focusing on this part today. Our work is on the other side of this, which is learning-based methods. And even in learning-based methods, the most popular way of doing this is learning visual representation for a point on Earth. So I will talk about some prior work, and it'll be useful because we build directly on top of the prior work. So one of the state-of-the-art methods for doing this is called SatClip, and this was published in 2025 AAAI. And the idea is actually pretty simple, but really powerful. So the high-level idea is that let's take this geolocation and try to learn a representation that has information about the visual contents that you would see at this location. So how you do this is you first start by gathering a bunch of data. So you have a bunch of latitude-longitude points, and then you have co-located satellite images gathered across the globe. And the idea is to just have a contrastive training kind of setting. So you have a location encoder that ingests this location information, and you're generating your location embedding. And on the image side, you pass the image through some really powerful pre-trained image encoder, which remains frozen throughout the training. And then you have this projection layer that is then going to fine-tune this feature in order to fulfill the contrastive objective or the influence objective, right? And it turns out that at the end of the training, you have really well-aligned space where the location and co-located images are well aligned to each other. And so once you have some downstream task and you have some downstream locations, you can take these locations, feed it through your location encoder. That is going to give you much more powerful representations. And then these representations are going to go into your downstream learner to solve whatever task it is that you're interested in. And this is where we start our work by looking at this as the foundation of our work. So this works really well. The authors show that experimentally this works better than most of the methods that existed before this. But how we start thinking about it is that when we look at contrastive training, we usually see it in image-text domain, image-to-image domain, text-to-text domain. And is there something missing when we try to directly apply this to this very weird setting of image and location? So let's look at it from a little bit of information theory perspective and see what's happening. So if you look at these final layers that we are learning in this process, usually these final layers are capturing shared information between the two modalities. This is because you're maximizing a lower bound on the mutual information. And so papers have shown that at the end, what usually tends to happen is that the information content in these final layers tends to be just the shared information or the intersection of the information between the two modalities, which in our case is the satellite image and the location. And so although this only captures shared information, this setting is still useful under one very important assumption, which is called multi-view redundancy. So let's look at what that is. So multi-view redundancy is a property that the shared information between the modalities is almost exactly what is relevant to solve a downstream task. So if we take an example, so let's look at this Venn diagram and assume X1 is modality 1, you have X2 modality 2, and Y is the task. And let's assume that S is the shared information between the two modalities. And so in the multi-view redundancy assumption, you assume that the shared information is almost all the information you need to solve the downstream task. So when you have learned this contrastive training, you can solve a downstream task effectively because all of the information that you need has been preserved at the end of your training. However, there are situations where this assumption gets violated, and then these representations are not will be a little bit suboptimal for your task. And that setting is usually referred to as multi-view non-redundancy setting. And this happens under two conditions most of the time. So one is that there is low shared information between the two modalities. And so the eventually learned shared information is just low in volume or low resolution. And the second condition is that there's high unique information in one or all the modalities. So the unique information is most likely not preserved in your final representations. So if there's high resolution information in the unique modalities, then you also lose a lot of that information. And so from this lens of multi-view redundancy, we make some hypotheses about the image location contrastive setting. So first is that the shared information between image and location is really low resolution. And second is that there's valuable task relevant unique information in the image modality itself, which gets lost in the contrastive training. And this makes sense to us because image is usually really dense information content, whereas the location coordinates are not. So there's definitely a ton of useful information in the image itself that gets lost in the contrastive process. And so with those two, we conclude that location image is a multi-view non-redundancy setting. And what that essentially means is that the representations that we get by training this in a contrastive fashion would also be suboptimal. So with that in mind, let's look at this from the perspective of what's from information loss and what's happening in the contrastive training. So we have this image that is passed through this pre-trained image encoder, and we get these really high resolution image features. But as you're trying to align these features to the location features, all that we end up preserving is this low resolution shared information. And so there's a huge amount of information loss that happens in between right here. And the essential problem that we try to solve through this paper is how are we going to estimate the lost unique information or the lost unique information in the image domain? And we start by looking at some inductive biases of satellite images. And we think there are two interesting things that happen in satellite images that we can leverage to solve this problem. So first of all, there is high redundancy in the visual information content between different satellite images. So if you look at minute details, of course, there are going to be difference, but from a large semantic perspective or structural perspective, information tends to be really redundant when you look at a bunch of satellite images across the world. And then the second thing is that satellite images exist in a closed set. Again, so if you want to look at all the satellite images from a certain sensor across the world, there's only so many, it's a limited set. And that means that it's easier to estimate the visual features that span the entire modality of satellite images. And so with that, our main goal is embedded into this statement that we can estimate the visual feature of any point by just using a small number of represented images, satellite images that are spread across the globe. This might not make too much sense at this point, but hopefully this will get clear as I go into a little bit more detail of our approach. So with all of this setup, I'm going to now go into our method range. So range stands for Retrieval Augmented Neural Fields for Multi-Resolution Geo-Embeddings. So for this, what we do is we first sample about 80,000 satellite images from across the globe. We save low resolution and high resolution features of these images in a database. This will again be, I'll explain this in detail in the next slide. And finally, we construct a retrieval system to estimate the lost visual information at any point using just the images in the database. And these images are not that high in numbers because of the inductive biases that I mentioned in the previous slide. So this is the entire framework. So we start with the same SAT-clip kind of training regime. We make no changes to this setting. So all of our method is post-training. So we have this alignment between the images and location, and we have preserved this low resolution shared information, right? So after this, we're going to take the 80,000 images that we collected across the globe, and we're going to pass it through our image pipeline. So we can get two different kind of features from this pipeline. So there's this green features, which are the low resolution shared information, and that are going to be our keys in the database. And then we also have these high resolution information, high resolution information that comes from these orange features, and that are going to be the values in our database. Once we have that, well, let's jump onto the inference stage where we have some query location. We're going to pass that through our location encoder and get the query embedding. And this query embedding is going to query into our database. And using our range function, which I'll describe in the next slide, we're going to compute an estimated visual information at that location. And this estimated visual information gets added to the shared information, which is then used as the representation to be fed into the downstream model. Okay, I'll go on to describing what the range function is doing. So in range function, we're trying to estimate the visual features by combining the visual feature across the database by their association, or more specifically, their semantic association with the query location. So let's assume that small gi is the query location, capital GI is the shared information, and capital SFI is the true visual information. We define a retriever function R of tau GI, which gives us S hat, where S hat is a noisy estimate of the true visual information. And then this noisy estimate of the image information gets concatenated with the shared information to give us the final feature. To expand on the range equation a little bit, what it eventually boils down to is that for any given query embedding, we are going to compute its similarity with all of the keys in the database. And based on the similarity metrics, we're going to average across the values of the entire database. And so eventually this just ends up looking like some sort of attention computation between the query, key, and the values. And what this attention is eventually giving you is that if you give me a location as a query, then I'm going to represent that location as a weighted sum of high-resolution visual features based on semantic similarity. So that is the first part of our approach. Secondly, since we're estimating visual information and we're in the geospatial domain, we can also estimate visual information based on geodesic similarity. So again, let's assume that you have this red point as the query point. It really makes sense that if there are points that are geospatially close to this red point in your database, then the visual features of this red point should be similar to all of the points that are spatially close to the red point, right? And so this can also be leveraged to estimate the visual features. So in Range Plus, we estimate a visual feature by combining the visual features across the database, not using semantic association like we previously did, but rather by using spatial association with the query location. And so what that means is that we add a couple of new variables into the original range function, where the first line that I showed previously is computing visual information based on semantic similarity, whereas the second line approximates the visual similarity based on spatial similarity. And the contribution of these two different things is controlled by this beta parameter. And beta will end up being really important, as it will allow us to add spatial smoothness to the embeddings, which we'll see in some of the upcoming slides. So with that, I will move on to some of our results. So the experiments are essentially that we take a location encoder, we take locations and get their representations, and then we use those representations to solve a bunch of geospatial tasks. Like these three are, the first three are classification tasks, and the last four are regression tasks. The first thing I will point out here as direct, which is directly using the 2D latitude-longitude coordinates, performs really, really worse when comparing to almost all of the other methods. But when we look at our range, we have significant boost over the state-of-the-art methods. And what this tells us is essentially two things. First, that our approach of estimating the visual information does work, and we're getting meaningful estimates for the visual information of a location. And secondly, what this also tells us is that our initial hypothesis that the image location is a multi-view non-redundancy setting is also probably accurate, because adding that visual information is allowing us to solve the downstream tasks much, much better, right? Secondly, we do some experiments with fine-grained species classification with GeoPrior, and this task is that you have images of species and you want to classify those images. But rather than just using the image, you also want to add the location of where that image was taken. And we see in general that adding the location boosts the performance by significant margins. But even here, we see that our range models performs really, really well. Finally, let's come to visualizing the embeddings. So these are just ICA plots of the embeddings, where we take the location embeddings and then use the first three components and then use them as RGB channels. And the key takeaway from these is that range tends to be able to capture much more high frequency information as compared to some of the other methods. And this high frequency information is definitely coming from the visual information that we have explicitly added into the embeddings, right? We can also look at what is the contribution of the beta parameter. So like I said, beta allows us to control the spatial smoothness of the embeddings. So at beta equals to 0, where we're estimating the visual features purely from spatial similarity, we end up getting very, very smooth kind of features. Whereas as we increase the value of beta, we see that the features tend to be more high resolution. And we also quantitatively show that. So I won't get into the details of the task, but there is a task called checkerboard, which allows us to control the resolution of the task. So this is a very low resolution task, and this is high resolution task on the right-hand side. And it turns out that, first of all, range outperforms all of the state-of-the-art methods by good margins across all of these resolutions. But the other interesting part is that you want your beta to be set to really low values if your task resolution is also low. And as the resolution of the task increases, you also want to increase beta because you want higher frequency embeddings to capture the high frequency differences that you see in the task. And so with this, we presented location embedding that can be computed at different frequency that has both low resolution shared information and high resolution unique information from the images. And just the final conclusion takeaways is that GeoAI is a rapidly growing field, and there is a good amount of interest in having good foundation models to process geospatial data. Methods that are designed for other modalities, sometimes, but not always, can be suboptimal when applied directly to geospatial data. And so in this work, we identified that there is an issue of multi-view redundancy assumption in the location image setting. And then we used some inductive biases from geospatial data to design a retrieval-based system that circumvents this issue. And our location embeddings demonstrate superior performance across the board when compared to state-of-the-art methods. And there's a lot of work happening in the geospatial field, and almost all of them use the geocoordinate as some data in some form, and hopefully our embedding method can help them boost the performance in whatever downstream applications that they are interested in. Right. So finally, I'd like to thank all of my co-authors in this work who were immensely helpful, and my wonderful advisor, Dr. Nathan Jacobs. Yeah, I think we are on time, 20 minutes. These are all of our models, all of our code is released online, so feel free to try it out. We have uploaded everything in Hugging Face for easy to use. So if you have any questions, I am willing to take them.